Hello everyone, I'm Sancaktar and I'll be presenting our paper End-to-End Pixel-Based Deep Active Inference for Body Perception and Action that I've worked on together with Pablo Lanillos and Marcel van Gerven from Donders Institute. So this work is motivated by a neuroscientific theory, Friston's free energy principle. The idea is that the human brain has an internal belief of the body state and a generative world model that delivers predicted sensations given your internal belief. The idea is to maximize the model evidence by minimizing the so-called variational free energy term, which is an upper bound on surprise. So you want your predicted sensations to match the sensory input of the real world. And you can achieve this in two ways. First is perceptual inference, where you update your internal belief, denoted here by mu, so that it matches your sensory observations. And the second way is through active inference, where you act in the world to resample the sensory data so that what you think you should be seeing matches what you actually see, thus minimizing the prediction error. So these are interesting ideas to apply to robotics, not only because it's biologically motivated, but because they formulate action and perception into a single framework. Robots need to deal with errors in model, as well as sensory noise, and they need to adapt to changes in the environment and the body. Free energy optimization offers a solution to these challenges. The idea of applying free energy optimization and active inference to robotics has been explored in the literature before, and you can find some references to previous work here. We will focus particularly on Oliver et al.'s work, where they use joint encoder values and 3D coordinates of the end effector to perform reaching and tracking tasks via free energy optimization. However, the internal model in this case relied on predetermined forward kinematics. In our work, we use deep learning to scale the algorithm to deal with high-dimensional inputs, namely images, so we can achieve dynamic body estimation and goal-driven control in humanoid robots using only monocular camera images. This gave rise to our PixelAI framework, pixel-based deep active inference, where our sensations are camera images. The internal belief of the robot corresponds to the estimates of the 4 joint angles of the robot's left arm, and we need a visual forward model that would output a prediction of a camera image given an internal belief value of the robot. This corresponds to the generative world model we mentioned before. In order to learn this mapping, we need a nonlinear function approximator. To this end, we used a deep convolution decoder that you see here. And once this mapping is learned, we can perform a forward pass through the network to get the predicted sensation. And this predicted image can then be compared to the actual camera observation in the real world. And then we use the visual prediction error to perform free energy optimization and update our internal belief values and/or generate action values. A very important component here is the orange term, the derivatives of the network output with respect to the network inputs, because they describe the transformation from the pixel domain to the joint space. And we can get this value by just performing a backward pass through the network, where the idea is the same as in backpropagation. For our experiments, we use the Aldebaran Now humanoid robot, both simulated and real. And the inputs for PixelAI were the bottom camera observations, as you see here. And we trained a deep convolutional decoder, the architecture of which is shown on the slide. Our input is 4-dimensional, and it's the joint angles. And then the input goes through 2 fully connected layers, followed by a series of transposed convolution and convolution operations. And then we get an output image. We trained this network on 2 separate data sets, one for simulated and one for real now. And in both cases, the network output had only 1 channel since we converted everything to grayscale images. We performed 2 separate types of tests for PixelAI, perceptual and active inference tests. To this end, we created a benchmark where we generated 50 random arm configurations, a subset of which is shown here. And then we performed 10 different sets tests for each of these core configurations using starting positions with 3 different levels of random perturbations. And the difficulty of the task increased from level 1 to 3, as illustrated in the examples on the slide. For the perceptual inference tests, the goal is to achieve dynamical body estimation. So here we set the robot arm to a certain position and it stayed there throughout the test. So the sensory visual information as well as the proprioceptive information stayed the same. And then we set the internal belief to a wrong value by adding a perturbation to the actual joint position. What we want is for the internal belief value to converge to the true joint angle positions by minimizing the visual prediction error between the camera image and the predicted sensation. So here the faint arm position is the true joint angle position, whereas the darker image is the perturbed initial prediction of the robot. So here the results show that via free energy optimization, the predicted image converges to the true position as the internal belief of the robot converges to the true angle positions. The robot can successfully minimize the initial error that we introduce via perturbation. So here are the benchmark results for perceptual inference. On the left side, the visual prediction error between the camera image and the internal prediction is shown. You can see how the error decreases over iterations of free energy minimization for all 3 levels of the benchmark. And on the right side, you see the decrease in error between the internal belief and the true joint angle values. Since different joint angle combinations can have very similar looking camera images, there is a local minima problem. This issue is most prevalent in level 3 tests which have the highest difficulty, hence the larger joint angle error you see here. So here are some perceptual inference examples from the real now robot. And on this slide, you find the benchmark results for the real robot compared with the simulated robot results, specifically on the L2 norm of error between the internal belief and the true joint angles. And as you can see here, the real robot results aren't as good as the simulation, which is expected since the images in the real world are noisier, for example, due to lighting differences and the reflective surface of the robot. So in the second set of tests, we performed image-based, goal-driven control using active inference. So the faint arm poses here are imagined arm positions. So these are our goals in the visual space. And just as before, the initial start position is a perturbed version of this goal with, again, 3 different levels of difficulty. And in the beginning, the internal belief is set to be equal to the current joint angles of this initial arm position. And what we want is to generate actions via free energy optimization so that the robot arm moves to this goal position. Here are 2 examples. And what happens is at each time step, the robot's internal belief gets updated in the direction of this goal, visual attractor, which causes a mismatch between the internally predicted image and the actual camera observation. To compensate for this, an action is generated to move the arm in the direction of this internal belief until iteratively the internal belief and the actual arm position reach this goal. And the actions here are generated from representation without an explicit policy. So here are the benchmark results for active inference. On the left side, you see how the visual error between the goal and the camera images is decreased as the arm iteratively converges to the goal. On the right side, you see the decrease in the norm of error between the goal position and the current arm joint angles for all 3 benchmark levels. As before, due to local minima, we have the largest error for the level 3 tests. Okay, and here are the results of active inference with the real robot. There is mechanical backlash in the actuators of the now robot, as well as noise in the sensors. Therefore, the results aren't as good as in the simulation. To conclude, we have scaled up active inference to deal with high-dimensional inputs by incorporating learning with neural networks. We have provided a proof of concept that we can perform image-based dynamical body estimation and goal-driven control. As future work, we want to explore applications to industrial tasks as well as multimodal systems. We also want to use more abstract representations of the body that will allow us to capture the complexity of the real world. And with that, I want to thank you for your attention.